go ahead and let the open up. Good afternoon, Advanced Kentucky AP Physics students and teachers. We're starting our third AP Physics online content review session to hopefully help you get ready for the May 14th AP Physics exam. Today's topic will be conservation laws. And I realize for those of you who may be taking AP Environmental Science, this is a completely different meaning of the word conservation laws, interestingly enough. And I think any environmental science students who might be here might be disappointed, but we are gonna go ahead and do this the physics way. Our presenter is Chad Rader from Madison Southern High School, who is a wonderful Advanced Kentucky consultant. I'm Lou Akampora. Many of you know me and as a host and the Director for Science for Advanced Kentucky. We have a fairly intimate group today, so please be participatory. But don't use your microphones or your video, but do use a chat room, and I think Chad will have some polls for us. But I said it's a small group. A lot of the activity will be on the archived version, and this session will be archived at kyap2020.com along with Chad's notes. Without further ado, this will be Chad Rader from Madison Southern High School. Take it away, Chad.
Hey guys, so let's see here. Can everybody see my PowerPoint now?
Yes.
Okay. And okay, so here we go. We're going to talk about laws of conservation. Like Lou said, we're going to be talking about momentum and energy. So for those environmental science kids, this will be a little bit disappointing, but for physics, these are the two things that we talk about a lot, especially energy. I tell my kids that the AP Physics exam, if you really tried, you could probably almost do every single problem on the exam using conservation of energy. Some of them would be ridiculously difficult by doing it that way, but you could probably do them that way. So we're going to talk about momentum and energy, and yeah, let's just go ahead and jump right into momentum. So here's your relevant momentum equations. Of course, you have momentum is equal to mass times velocity. Something that you want to remember with this equation is that velocity is a vector. So momentum velocity being a vector, it does have direction. That's very important so that you can have positive or negative numbers there. And the change in momentum, which is, as we know, force times time there. So that's also an equation that we're going to be using quite a bit. And then the angular momentum stuff, we're not going to get into this as much. That would be probably a whole nother session. But angular momentum, we'll at least touch on it, which is the moment of inertia of an object multiplied by the omega, and omega is the angular velocity. And changing angular momentum is when you apply a torque over a time, okay? So these are the relevant equations that we're going to be dealing with. These are on your equation sheet, which this year I don't think is quite as important as it has been in the past. In previous years, I always drill these into my kids' heads over and over and over and make sure that they know them inside and out and upside and down and all that stuff. But this year, I think with doing no multiple choice, I think you have a little bit of time at least to kind of be able to stop and think about what you're doing. So the equations here, while I recommend that you have them memorized, you will have a little bit of time to be able to soak in an equation sheet if you happen to have that lying next to your keyboard while you're taking this test. So I think these are super important. I think you should memorize them. But if you don't have them memorized, I don't think that that's the end of the world. Whereas in previous years on any multiple choice test, I would definitely have my kids, we actually do equation quizzes and I make sure that they have them memorized. But let's talk about this change in momentum thing, which is a force over time, a force exerted over a time, okay? So I have this first graph here. You will see a ton of these graphs throughout multiple choice questions. AP Physics writers really like this. Now as soon as you see this, you're gonna come over here and you're gonna say, oh, here's a force. So this is probably a graph that has been acquired somehow by some kind of force meter, whether it's a springform scale or an actual force meter or something like that. You may have done something like this with your vernier if you did that in class. If not, that's okay. That's okay. Because this is force times a time interval, what we're going to do with this graph, and you're going to end up doing this a lot, I think, in these type of tests, is you're going to actually see here that this basically makes a line here. You can do a line of best fit type of thing. And then the area between that force and the axis here, the area right here, and you'll have to excuse my my drawing of this rectangle, but the area right here is actually force, which is over here on this axis, multiplied by a change in time, which is this axis down here. So this area under here is a great way for us to calculate the change in momentum of an object. So this happens quite a bit on the AP exams. They really like to do these graphs. And something I want everybody to notice here is that if we have this force and this time, what we don't have is a direction for this force. So while we know that if this is the net force on an object, while we know that this object would be changing its momentum, it would be speeding up, it would be slowing down, one of the two, we don't know which one it's doing, right? We don't know which direction the force is. Is it in the same direction as the velocity, or is it in a different direction? So they like to be a little bit tricky there, and I want you guys to, just kind of see that and put that in your back pocket. That's one of the tricks that you're gonna probably need to use if there's a momentum question on this particular exam, and I suspect there probably will be. If you have something like this, another thing that you will see, I like to look for patterns on the AP exam. So I like to see questions that they ask similar questions quite a bit. So here we have another graph, just like the one that we were just looking at, and we'll say that this is the graph acquired from a force probe on the front of cart A. Well, what does the graph, if there was a force probe on the front of cart B, what would that look like? And again, we're going to say, even though this is a momentum problem, you need to know that that graph would look exactly like this, except it will be inverted, because the direction is the other direction. So whatever force is being exerted on this cart, you're going to have, according to Newton's third law, right? Newton's third law, you're going to have an equal force. So at any given time, you will have an equal force, but the direction will be the opposite on this cart, which is really cool because if the area under this graph gives the change in momentum for this cart, then the area under this graph will give the change in momentum for this cart. Okay, and those two changes in momentum, if this cart changes its momentum by this much, and then this cart changes its momentum by this much, if we can include those two carts in one system, we can say that one cart is gaining this amount of momentum and the other cart is losing this amount of momentum. And there is where we get that whole conservation of momentum, which is what we're going to be talking about. The conservation of momentum for the system. Now, this cart individually, its momentum is not conserved. This cart individually, its momentum would not be conserved. But for the system, for both carts, then is where you get that momentum conservation. Okay, and we're going to talk about that a little bit more, but I like for everybody to see this type of thing. Okay, these graphs right here, like I say, are very, very, very prominent on the exam. Okay, so here's our first poll. We got 3 experiments here. We're going to call this one A, and this one B, and this one experiment C. Which one of those experiments do you think would cause the greatest change in momentum? Would it be experiment 1, which is A, 2, which is B, or 3, which is C? And if you don't like any of those answers, then go ahead and say D for whatever reason, and we'll discuss why you may not like some of those answers.
And this is for the entire 20-second interval, presumably, right, Chad?
Yes, I'm sorry. Yes, for the entire 20-second interval. I'm sorry.
Okay, just making clear. So we've got most of the respondents coming in, so I'm going to end the polling in 3, 2, 1.
Okay, awesome. So most of us are, well, 57% of us are on D here, which is cool. We got 29% with A and 14% with B. Now, why do we like D the most? Well, overall, what we're going to do, and I know that the pressure's on here, right? But what we have to do is we have to first, for this 20-second interval, we do experiment 1, and then we have to find the area under this triangle, and that is going to be the change in momentum in experiment 1. And then we have to go back and we have to, let's see if I can change the color of my pen. I don't, pointer options, pen. Well, I don't guess I can. We can have to find, for experiment 3, we have to find this large triangle right here. And then for experiment 2, we have to find this area under this dotted line right here, which is just a rectangle. Now, since we're doing the poll and you guys don't have a whole lot of time, I know that you're like rushing on that, but the area under this large triangle, the area under this triangle and above this axis, and the area under this line and above this axis are all the same. So the change in momentum caused by each of these forces over this 20-second interval is all the same. Now, let's see, I'll erase everything. If we just looked at, say, 10 seconds, the first 10 seconds, then in experiment 1, there is a much larger change in momentum than in experiment 2 or experiment 3. Because the area, well, no, I take that back. In experiment 3, but in experiment 2, this area and this area are still the same over the 10-second interval. So what's happening here is you just have a constant force applied for 10 seconds, or you have a force that starts out really small and keeps getting bigger for 10 seconds. But the average force for that 10 seconds is going to be the same for either of those experiments. But this experiment here, experiment 3, well, it starts out small and then it doesn't get as large enough to have an average that is the same as those two. So here we have cart A and cart B, and we got a little different graph. They like to mix things up. The AP board, the AP folks, they like to mix things up. If cart A and cart B are the same, okay, so they have they're exactly the same. They got the same mass. We're on a frictionless track, that kind of whatever. Which one of these two, cart A or cart B, do you think would have a larger change in momentum? Or we'll do this exactly the same as we did the last poll. You want to do cart A, cart B, or we'll do same. So A for cart A, B for cart B, or C, they're the same.
And we seem to have enough polls, so I'm going to close this in 3, 2, 1. Okay.
All right. So we've got we're 38% on B and 63% on C. This was a lot tougher. And here's the way that we have to look at this. We've got acceleration over here on the axis. And we've got time over here on the x-axis, acceleration on the y, time on the x. But we can say that force, which is what we're used to having over here when we're trying to deal with impulse, we're going to say that that is equal to mass times acceleration. So really, this acceleration being over here on this axis, if we did this kind of number, we can see that the mass is just a multiplier, right? And we know the mass of this cart and this cart were exactly the same. So really, this graph or the force time graph that we've been looking at, even though they're not equal, we do have they're proportional, right? This only works if this cart and this cart have the same mass, okay? Or if we use the same cart, if the AP board would have done something where this is lab A and lab B, and they were done with the same cart, we could have had this same thing and they would have asked, hey, which one has the larger change in momentum? Well, the area here and the area here are the same if you take the time and find those areas, okay? Now, I do want to point out that these dots are kind of all over the place right here and all squiggly, and they don't make these perfect straight lines like we want. We want a perfectly straight line up and down. That way we can find the area of that triangle really, really, really easily. But because this is experimental data, the AP questions will have the dots kind of being a little up and down to represent the error that would happen in a lab. But when you get your test, you need to just go ahead and smooth that out, okay? It's basically just doing lines of best fit or functions of best fit or curves of best fit, whatever you need to do, okay? So let's look at this one. Now this one's a little bit tougher. We got a spacecraft that is 400 kilograms traveling in a straight line in a positive directions. The engines are fired and a force is exerted on the spacecraft. If this is the force time graph, then what is the net change in speed of the spacecraft over these 4 seconds right here? And I'll show you guys how to do this. So we're gonna, first of all, again, the types of shapes that we have on this test, we're gonna do a lot of triangles because a triangle is really easy to find the area of, right? In the calculus test, in the C test, then you get some really wacky shapes. But here, we're going to smooth this out. We're going to kind of make a triangle here. We're going to do the same thing here. And this one looks a little bit like a rectangle to me. Okay? Now, the reason that I included this one is this is a positive change in our momentum. That means during this time, when this engine was fired on this thing, the rocket was speeding up. So speeds up, speeds up, speeds up, speeds up, speeds up. And then right here at 2 seconds, we no longer have a net force. No net force. No net force means no acceleration. So we're not, so speed up, speed up, speed up, speed up, speed up, no acceleration. And then we drop down here and we have a negative net force. Well, what does that mean? That means slow down, slow down, slow down, slow down, right? So just thinking of this from a kinematics type of perspective, which my students tend to have a little bit easier time with, this is a positive force. We're pushing on something in a positive direction. That causes that thing to speed up. Okay, now we're not pushing on it. Nothing's pushing on it because it's out in space. So we have no friction or anything like that right here from 2 to 3 seconds. So we're not speeding up, we're not slowing down, we're just coasting along here. And then all of a sudden we've realized we're going too fast. So then we hit the brakes and now we have a negative force right here, which is slow down, slow down, slow down, slow down. And I'll save you guys from doing the math here because in the interest of time. But what we do is we find the area of this triangle and then we subtract, because this is a negative, we subtract the area of this rectangle right here. Now the rectangle is pretty easy. The triangle is pretty easy, but in the interest of time, we're just going to kind of glaze over that. And you get a positive 0.125, and this is the closest number to that, which is another thing that you guys don't have to worry about because you don't have multiple choice. But in years past, you would just have to pick the number that is closest. This year, since it's all free response, they'll be taking numbers, and luckily any math on this thing is going to, you should be able to do it without a calculator this year, which is nice. Okay, let's look at this one. I really like, I really love this problem. You got two identical spaceships traveling in deep space, and they're far away from any planets or stars. Now that's important because that means, of course, you've got no planets, no stars. That means no gravity, nothing, no outside forces. The ships are traveling in the same direction. The slower one is behind the faster one. The ships are connected by a cable attached to a spool. Cable goes outside, makes longer, shorter as needed. The cable is going to bring the two ships the same speed to transfer cargo. Now, here's the question. Is there a force on one of these two ships other than this cable? Okay, so they've got a cable that's attaching ship 1 to ship 2. So if you imagine that, and I'm not even going to try to draw spaceships here, but here's ship 1 and here's ship 2. And then they have like some kind of pulley on top of this ship, and it's connected over here to this ship, right? And when this one here starts pulling, then this one will start coming together. They'll start coming toward one another. And I know my drawing is horrible there. Please don't. I tell my kids all the time, it's not an art class, right? So if I only look at this ship, okay, so now we're going to just talk about systems. I'm only talking about this ship. Its momentum is going to change because there's an outside force on it right here. So I can look at its velocity and how much its velocity is changing. The change in velocity is the slope here, which is really kind of cool. It's another way that they can ask you about a momentum of an object. Here we now have a velocity time graph. Okay, so if the velocity is changing, we know the momentum is changing, and the slope of that velocity is acceleration, which is directly related to the force. Well, if this is the only force on this ship, then this should also be the only force on this ship. And if they have identical masses, then this should have an identical slope, okay? It's in the opposite direction because the direction of the cable is in the opposite direction. The direction of the force is in the opposite direction. So what we should have is we should have a slope down like this and then an equal slope up like this for ship 2. But we don't have that. This ship has got a bigger slope here. So what that's telling us is ship 2 has, or ship 1, we're not really sure which one, has another force on it other than just this cable. If they're identical ships with one force on them that is identical, then this slope and this slope should be identical, except for one would be, you know, a positive slope and one would be a negative slope. So one of these has something else acting upon it because it has a larger change in velocity than the other one, or a smaller change in velocity. We're not sure what's acting on them. We're not sure the direction. And that's a little bit of vagueness that they will include in these questions just to kind of throw you off. Okay, so here we'll do this poll real quick. Here's a force exerted on a box. Sorry. Here's a force exerted on a box. At which time interval, 1 to 2 seconds, or 2 to 4 seconds, or 4 to 6 seconds, would this box have the greatest change in momentum?
And I think it's important to really see what's being plotted on the axes here. So we've got about most of our respondents polling. So I'm going to go ahead and end the poll in 3, 2, 1 second.
All right, very good. We got 6 people going with C. Good. So on the axis here, as Mr. Akampora was saying, on the axis right here, we have on our x-axis, we got force. On our y-axis, we've got force. On our x-axis, we've got time, and this is force, time. So for the first 2 seconds, we get this area right here, and that is our change in momentum. For the next 2 seconds, we get this area right here. That would be our change in momentum. And then for the last 2 seconds, we get this area right here. And this question, which is cleverly disguised, right? This question looks like it's incredibly difficult, but if you know just this equation, and you can apply this equation, then this question is really asking, which one of these is bigger? This, or this? And anytime you can, anytime you know enough physics to be able to say, okay, well, what they're really asking is what's bigger, A, B, or C, and you're looking right at it. Oh, well, C is definitely the largest shaded area. Then what you're doing is you're getting yourself some really, really, really easy points, and those are the points that you want to get. Okay, you got to be able to get all the easy points, and then that's what gets you the 3 on the exam, and then all the hard points. This is what I tell my students: all the easy points get you the 3, all the hard points get you the 4, and then the really hard points are the ones that bump you on up to the 5. So make sure that stuff like this doesn't like throw a wrench into your test taking. Okay, so moving on here. Open systems versus closed systems for momentum. Open systems, external interactions. Closed system, no external interactions. Okay, and that is a grand oversimplification of an open and closed system. Okay, so I like to tell my kids that this is kind of a convenient lie. There's a lot more to it than this, but this is the way that I do things, just so we can cheat and get the right answer. Okay, so here's some of the types of questions that they want to ask on the AP exam. 100 years ago, they didn't used to ask these types of questions as much. They would just say, okay, here's block X, here's block Y, here's the momentum of block X, here's the momentum of block Y. What happens when they collide into one another? Okay, now here we are taking this exam. They like to ask a lot more conceptual questions. So here's what the type of stuff that they're going to ask. Instead of saying, okay, momentum is conserved for this whole system, which it is, they like to ask about just block X. Is block X's momentum conserved during this collision? Well, it's moving here and it's moving slower here. So no, block X's momentum not conserved. Same thing with block Y. If I only look at block Y, which is an open system, block Y interacts with block X, okay? So it's an open system. It's interacting with things outside of the system. So block Y's momentum, not conserved. Block X's momentum, not conserved. If I look at them together, though, there's nothing interacting with block X and block Y that is outside of block X and block Y. Okay, so block X has something outside of it acting on it. That would be block Y. Block Y has something outside of it, block X. But this whole thing, block XY, you know, if I look at both of them together, there's nothing acting on them outside of both of those blocks, okay? So the momentum is conserved. I know that's a little bit confusing. The momentum is conserved if I look at both blocks together. But if I look at each one individually, the momentum would not be conserved. And that's pretty important. The past couple of years, AP has kind of harped on that just a little bit. The momentum here, not conserved. The momentum here, not conserved. The momentum of this whole thing, however, is conserved. And you've probably done a ton of those problems. That's why I haven't included as many of them in this presentation. You've probably done a ton of, okay, block X collides with block Y and they stick together. What's the velocity of block X and Y once they collide and stick together? Or you've probably even done a much more difficult case of block X collides with block Y and bounces off of block Y. In both of those cases, momentum for the whole system is conserved, okay? But the momentum for block X is not conserved, and the momentum for block Y is not conserved, okay? So that's something that's very important that you need to remember, okay? Because I'm not saying they will ask that. I'm not saying that at all, but they do like to know that you can define a system, okay? And that's very important. Being able to just say, just look at blocks at X and say what's going on. Just look at block Y and say what's going on, okay? I feel like a lot of my classes, I'm just sitting here talking to myself. It's kind of weird. So here we have an open versus closed system, and this one's going to include not only just the collision right here, but it would also include a little bit of energy too. So let's just think about the momentum of block X, just the momentum of block X, okay? So here, what would the momentum be? Well, it's just sitting at rest on top of this hill. Momentum is 0. And it comes down this hill. Well, there is a force acting upon it for an amount of time, force times time, so its momentum changes. Now, the force is a wonky force because it's gravity, but it's just a component. So we have to do all kinds of crazy math here, but that's not relevant. The point is, if I only look at this block from here to here, its momentum increases this whole time. Now, we can break this into sections, and that's really what I like doing. So we're going to go from here to here. That's going to be one type of problem, okay? Oh, how much faster is this block going as it comes down this hill? It keeps getting faster and faster and faster. And you have to do conservation of energy, which we're going to talk about in just a minute, in order to do that. But then when it gets right here, when block X gets right here, and it's on a level piece of this table, and it collides, at that moment, we can just say block X and Y are their own little system here because they're on a level table. So gravity is not causing block X and Y to speed up. It's not causing them to slow down. So there's no outside forces causing changes in velocities. So right here, we can do conservation of momentum for the whole XY system. but only right there, because as soon as they leave the table, looky here, we've got gravity acting upon both boxes again. So we don't get to do that whole conservation of momentum thing. Okay, so from here to here, well, we can't do conservation of momentum. Right here at this spot only, we can do conservation of momentum for these two blocks. And then as soon as they leave this spot, here we are again, we're being pulled down by gravity, so we don't get to do conservation of momentum there. So it's very important to see that this is an open system where gravity is pulling on it. Then right here, we can kind of close the system for just a split second in time. And then as soon as they fly off, we have to open the system back up because gravity starts acting upon these guys one more time on block X and block Y. Okay. And again, that's something that the AP board has kind of stressed. Can you define your system? Are you really good at defining those systems and figuring out what's going on? Okay. So I'm trying to get through some stuff here. We'll go ahead and skip this one. It's a collision thing. So, because we're at 2:41, I was going to do a poll here. So I'm going to try to get to energy. I've used a lot of time on momentum here. This is cart X and cart Y. They collide. I'll do this real quick, just kind of explain it to you. Here's the initial velocities of both cart X and cart Y. Here's the final velocities of cart X and cart Y. Another thing they like to do, of course, are these lab type of questions. And then they'll ask you, you know, how would you measure the velocity here? How would you measure the velocity here? And what additional information would you need in order to figure out if momentum was conserved during this collision? And the answer is, you want to look at this situation. You want to say, okay, well, what's momentum? And you know that it's mass times velocity. Well, I have velocities everywhere. What am I missing? Oh, I'm missing mass. So that's kind of what they do to you. And as long as you have, as long as you got a good grasp of the equations, just write down what variables you know, and the one that you don't know, well, that's the one you're missing. And then they'll probably ask you something like, how do you measure that? Well, in this case, you can measure it with a balance or a scale or something like that. So energy, I'm going to move on to that. Energy, here's your equations. Again, I'd ask all of you to memorize these equations. If you haven't, don't panic. But potential energy due to gravity, mgh, that's actually how it is. I think that's how it's listed on the equation sheet. Sometimes, and I don't remember if there's a delta H there or if they say Y. I probably should have copied that off the actual page. But potential energy due to elasticity is 1/2 of K, how far the spring is stretched squared. And then you have two types of kinetic energy. One is the translational kinetic energy. This is the one that you've seen since you were in 7th grade, right? Everybody talks about this one. Everybody knows this one, the 1/2 mv squared. The one that is not talked about, because this one's really scary, is the rotational kinetic energy, which is the 1/2 I omega squared. And again, we're not going to get very far with that one. Rotational stuff, I just don't have time for it. But the total mechanical energy of a system is just when we take all of these and we just add them all together. Okay, so you've got your gravitational potential plus your spring potential plus your translational kinetic plus your rotational kinetic. And then this is always conserved unless there is a force out here like friction or something like that, the non-conservative forces, and then we would have to add non-conservative stuff. Okay, so you have this plus non-conservative. But this, within a system, we're always going to try to say the total energy is equal at the beginning and at the end of a problem. Okay, so like right here, this block begins at rest, sitting here, it's not moving. And you should know that we have M, G, and then this height, H. Okay, that's the only kind of energy this block has. It's not moving, so it's not moving translationally, so it doesn't have 1/2 mv squared. It's not moving rotationally, so it doesn't have the 1/2 I omega squared, and there's no spring to be found. And if this thing comes down to the bottom of this ramp right here and then slides some distance d and then stops right here, well, the question is this an open system or is this a closed system? Well, we started out with this much energy and now we're down here and we got 0 energy, okay? We're not moving in any way, shape, or form. So this system has to be open. We have lost this much energy to something. And they'll often ask you, where did that energy go? Well, that means that this surface right here is probably a rough surface. And you've got friction, and the frictional force is doing work on the block, slowing it down. And then it eventually comes to rest out here. Okay, so this is the energy that we started with, and then we end with 0 energy. Now, in the interim, we could ask right here, if this is a smooth ramp, how fast would this block be going right here? And this is very important because this is a curved ramp. So a lot of my kids, when they first start out doing these types of problems, they're like, oh, I see a ramp and I see the height of the ramp. So they want to try to do some kind of crazy kinematics. But remember that kinematics don't work when you have a curve like this. So the fact that it's curved, as soon as you see a curved ramp like that, you're going to want to go ahead and do the energy route. Okay, energy is much, much, much easier on problems like this. Now, sometimes if you have a straight ramp, it behooves you to go ahead and do kinematics. But for the most part, I prefer energy in almost every situation. Energy's a little easier to deal with, in my opinion. Okay, so let's look at this one. Here, we've got a block on a compressed spring, and we're going to let go of it. And then it's going to slide up this ramp and come to a stop right here. Now, again, one of the things that they really, 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 really want you to do is to be able to define your system. So if I ask, what is the energy of the block spring system right here, then you can say the block spring system has an energy, because the spring is compressed, of 1/2 kx squared, depending on how much we compress the spring and what the spring constant is. The block itself, if they just ask you what's the energy of the block right there, well, other than, well, no, the block has no energy. The block's not moving, so it doesn't have any energy. Even if we let go of this and it slides all the way up here, okay? If you are asked, what is the energy of the block right there? Well, guess what, kids? The energy of the block while it's up on this ramp is still a whopping 0 joules. You have to define your system. And the only way that we get energy up here is if we specifically say that we are talking about the block Earth system. If you just say, how much potential energy does this block have? The answer is always 0. Okay, gravitational potential energy for this block is always, always, always 0. It has to be the block Earth system. You have to bring that into play. You have to have the Earth. Okay. I'm gonna here we have a rocket that has been launched up into the air, and the rocket keeps going faster and faster as it goes up into the air. And in this question, they were nice enough to define the system for you. They talk about the Earth rocket system. So as the rocket is going higher and higher and higher, you have the rocket up here, and then you have the Earth down here. And because they define that system, you can talk about the potential energy. And as the rocket gets higher and higher, the energy, the potential energy of the system increases. I'm sorry I'm rushing through these here, but I've got a couple more slides and we're down to just a little bit of time left. So the kinetic energy of the rocket itself, only the rocket is also increasing because it's going faster and faster and faster. So the total mechanical energy of the rocket, mechanical energy, that should say mechanical right there, the total energy of the Earth rocket system isn't changing because we have to change some kind of chemical energy into these things, but the mechanical energy is increasing. It's kind of a nuanced thing there. This right here, this is a question that was asked on an AP exam where they ask, where is this thing moving the fastest and where is it moving the slowest? Well, my students see this and they think, oh, it's a velocity question. Well, it's really an energy question, okay? So they're disguising velocity and energy, okay? So it's like, ha, 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 we're asking you about velocity. No, you're not. You're asking me, when does this block have the highest kinetic energy? Okay, and the only two types of energy that we're dealing with here is mgh of the block Earth. And then as it comes down this ramp, this mgh will become 1/2 mv squared. Right here, it's totally 1/2 mv squared. And then it just kind of goes back and forth between this and this. They're just bouncing back and forth. So the slowest part, other than when it's not moving at all, the slowest part on this loop is here, and the fastest part is here. And again, they like to do questions like that. And the area under, this time, be careful, I'm going to include this because this is, instead of a force time graph, which is what we were looking at earlier, this is a force distance graph. So you can do the same type of thing we were doing earlier, and this force distance area right here is actually change in energy. Okay, so you can do that exact same thing. So pay very, very, very close attention to your axes. Those are extremely, extremely important. Force and distance, whereas earlier we were doing force and time. So here we go. Let's just do this poll really, really quick here. If gravitational potential energy is looking like this, what does the kinetic energy of this object look like? If gravitational potential energy looks like this, what does the kinetic energy look like?
And even though there won't be any multiple choice questions on this year's exam, I think
We lost you, Lou. You muted yourself.
sorry, even though this year's exams will not include multiple choice questions, they will include, or creating graphs, they will certainly include interpreting graphs. And I think that this is an important question. So I'm going to end the polling in 5, 4, 3, 2, and 1 second. And it looks like we did pretty well. I agree with this one. Chad, how about you?
Yeah, perfect. Well, I guess I was wasting my time with that one, which is good. That's what I like to hear. I like to hear that I've wasted everyone's time with these. Yeah, just like Lou's saying here, we're not creating graphs on this year's, and we're not doing any multiple choice, but I am quite sure they will give you plenty of graphs that you have to interpret. And I know you guys already know this apparently, so I'm going to be wasting my time here, but right here across is the total energy. It's just going to be straight across like that. So you have to be able to add gravitational with kinetic to get that. That's really good, guys. That's awesome. Let's do this one. If there's only just a little bit of friction, which one of these is going to hit the bottom first and why? A, the block, or B, the sphere, and why? Just a little bit of friction.
And the same little bit of friction for both objects, right?
Yes, same little bit of friction for both objects, yes.
Okay, I've got a guess on this one.
I'm sure you do.
Well, I'm not sure about it. All right.
All right. So we're split on this one, which is tough. Okay, we're pretty much 50-50. So this must be a tough one. Well, which one's going to reach the bottom first? It's going to be this guy. Our block's going to reach the bottom first, and here's why. And this is kind of cool. At the top of this ramp, we have MGH. Once we get down to the bottom down here, all of this is going to be 1/2 mv squared and just a little bit of heat, okay? Just a little bit. Okay, so it's mostly going to be this. That's why there's just very little friction. That same little bit of friction is going to cause this guy to start rotating. Here I have MGH. And at the bottom, it's going to equal 1/2 mv squared plus, well, it's going to start rotating because of that friction. So you have 1/2 I omega squared. So this is the one problem I like to ask in my class, just to show that we have to kind of include this guy. Okay, once this thing starts rotating, we're going to have this. That means we have to have less of this. Okay, so that's kind of cool, I think. It allowed me to help my son win his soapbox derby racer thing when he was in Cub Scouts. We actually
a physics teacher for a dad seems like an unfair advantage.
Well, we actually did it with only 3 wheels, so we would have less of this. So you guys will appreciate that later when you have kids. On this one, if I drop this one, and these are all frictionless, if I drop this one, let this one slide, this one and this box A and box B will be moving the same speed when they hit the ground. This one's actually going to be going faster because it has an initial velocity, so it's going to only gain velocity. It'll gain the same amount of velocity as those two, but it's going to be in the Y direction and the X direction. So the actual highest velocity belongs to C. But A and B if we just look at those things, are going to have the same velocity when they hit the ground. And I think that's it for me. It is 3 o'clock, and I rushed through a little bit of that, but I tried to cover everything. If anybody has any questions, let's go and go ahead and fire some off. I'll see what I can do. If there's anything in the chat box for us, Lou, anything like that?
I think we did pretty well. We had a good participation on the polls, and I think a very strong group of students watching live. So thank you all very much, and thank you, Chad. I guess we'll sign off now, and I will go ahead and archive this. But good luck, and feel free to contact me, teachers or students. And I'm really proud that we're all taking the AP exam seriously, and have a good opportunity to show what you've learned. Have a good afternoon and evening, and tune in next week. Take care now.
Thanks, guys.